Bill Gates once said that the advance of modern technology is based on how well we can make it fit in without us noticing that we're using it in our daily life. A splendid morning, I bid to the panels. My name is Natasha, and I am going to present my final year project entitled to design a CMOS ring oscillator using 130 nanometer technology. And my project, I'm supervised under Madam Nohafizan binti Muhammad Hanif. Okay, and then as you can see, this is the contents of my project, and we are going to talk about basically 10 things. Okay, firstly, we're using portable electronic devices in our daily life. We're using them excessively, and we depend on them very much. And how does these electronic devices relate to my project? Well, these electronic devices, they contain integrated circuits, also known as IC. And the most commonly used form of IC is the CMOS, which stands for the complementary metal oxide semiconductor. A CMOS, it consists of the combination of two types of transistor, which is the NMOS and also the PMOS. Well, NMOS stands for N-type metal oxide semiconductor, and PMOS stands for P-type metal oxide semiconductor. And as you can see here, this is the schematic diagram or the most basic structure of a CMOS inverter. Okay, for my problem statement, how does this problem relate to my project and what I aim to solve? Okay, firstly, as IC designers, we are constantly concerned about low operating life of electronic devices as well as digital systems to sustain the rising market of electronic devices such as our laptops or our phones. Secondly, most ICs, when we use it, it consumes high power, or it has high power dissipation, and due to this problem, it can encounter more problems in the future, especially during reliability testing. Okay, essentially, I'm going to explain what my project is about. This is the most basic structure. This is the inverter NOT gate, and the inverter is what contains in my ring oscillator. Okay, let me explain first about my inverter. This is the symbol of the inverter. It has an output and it has an input. It has a very direct function. When the input has a high voltage level, then the output has a low voltage level. It is it has an opposite operation. Okay, and this is the truth table. Okay, and then for an inverter, how it works in a ring oscillator is that there are multiple chains of inverters in a ring oscillator. And a ring oscillator, it can only have odd numbers of odd gates. So you can have 3, 5, 7, and in my case, I'm making a 9-stage ring oscillator. Okay, here you can see. And for ring oscillator, it does not have any input. Why does it not have any input? Well, a ring oscillator can operate and it produces the inputs by noise signals. So you can see it has an output, then it has a positive feedback. It's like a circle, it's like a chain. Okay. However, as I've said, for the ring oscillator, it must only have configurations of odd number gates. However, if it is an even number gates, well, it can be used in a SRAM. It can be used as a data storage memory. So you can have 4, you can have 6, and it cannot be in a ring oscillator. Okay, next I'm going to talk about power consumption in CMOS circuit. Power consumption is inevitable in a CMOS circuit, or basically in an electronic device. For power consumption, it consists of 3 categories, which is the static power, dynamic switching power, and the short circuit power. For the static power, it is divided into 2, which is the leakage power as well as the standby power. Well, what is a leakage power? A leakage power is due to a leakage current. So when a transistor is in an off state, there is a leakage current due to reverse bias current. Usually, in an ideal circuit, in an ideal transistor, it does not have any leakage current. However, due to reverse bias, there is. And in one transistor, the leakage current value amount is very small. However, in one IC, there are millions or billions of transistors. That is why this small amount of leakage current, it can become a very huge value of leakage current. That's why it is important. And due to leakage current, there is leakage power. Next, for standby power. Standby power is due to when the transistor is operating, then there is current. There is current. It flows from the VDD, which is the power supply, to the ground. And because there is current flowing continuously in this transistor, there is also power. Okay. Next is for dynamic switching power. Dynamic switching power is due to the activity, the switching activity in a transistor. So when the PMOS or the NMOS switches from on to off, and also vice versa, then there is power because there is current. Lastly, the short circuit power. The short circuit power is caused by a fault or any faulty in a circuit. Okay, it has a very small value, so it does not really affect a circuit that much. So we can usually neglect it. Okay, and as you can see, this is the comparison of my research paper. I've chose 2 research paper that has 4 types of techniques, which is the static CMOS, the stacking, the novel sleep inverter, as well as the state retention inverter. And then this is the technology used, and this is the number of stages. Okay. Next, we move on to my objectives as well as my project scope. Firstly, I'd like to study the fundamentals of ring oscillator, which means that I'd like to know how a ring oscillator works. I'd like to know how many numbers of transistors in the ring oscillator. I'd like to know how much power it consumes, and also the size of an appropriate ring oscillator. Okay, secondly, I'd like to design a CMOS ring oscillator with 130 nanometer CMOS technology. Well, what is a CMOS technology? A CMOS technology is essentially the gate length of an IC. So you can have 65 nanometer CMOS technology, you can have 90. It depends, it varies, depends on the advancement of the technology in the industry. In MJII, we're using Mentor Graphic, which only has the minimum of 130 nanometer CMOS technology. Okay. Thirdly, my third objective is to analyze the results taken from the Mentor Graphic simulation, which means that after I do my simulation, I revise the parameters, I'll analyze the parameters, and I'll see what I want and the factors that are considered that I'll take. Okay. Lastly, I will carry out the optimization of ring oscillator. Optimization means that I take 2 different types of technique and I combine it, and that is basically my main goal, my main objective in this project. The benefits of my project, or the benefits of my device, is that firstly, it is sort of like a new invention or new optimization of an IC in the electronic industry, and secondly, it is low power device, and I am focusing on making my device low power as compared to all the research papers that I've read. Okay, we move on to the methodology related to my project. Okay, firstly, I'm using a software called Mentor Graphics software. And for Mentor Graphics, it is basically like one huge EDA software, which is the electronic design automation. And then in this EDA, I'm using a virtual machine called the Oracle VM VirtualBox. So once I open the Mentor Graphics simulation, I'll access this virtual machine. Then through this virtual machine, I am going to a new operating system called Linux. So Linux is it's the same as Windows, but it's a different. So when I open Mentor Graphics, I have basically 2 types of OS in my laptop. Okay, and this is the block diagram of the inverter. This is the most basic one, and this is my block diagram of the ring oscillator. As you can see, it's chains of inverters. So my ring oscillator only has inverters. So it's very basic and very simple. Okay. For the low power techniques, the first low power techniques I'm using is the static CMOS. Why am I using static CMOS? Well, it has the most basic structure, it's the most simple one to make, to design, and everyone understands how it works. And as you can see, I only use PMOS as well as an NMOS. So the Pmost value, it has a width of 2 micro, and the Nmost value, it has a width of 1 micro. So I take this one inverter, then I multiply by 9, so I get a 9-stage ring oscillator. So basically, this is how this works. The input is basically an output because, like I said, it does not have any input. Okay, next, moving on to my stacking method. What makes the stacking method different to the static CMOS method is that I add another Nmos transistor to the Nmos just now. Okay, if you can remember, my PMOS has a width of 2 micro, and my Nmos for the static has the width of 1 micro. However, for stacking method, the value of Nmos, since I add 1, so it's half of the original value. So now my Nmos value is 0.5 micro. So I divide it into 2. So essentially this is basically 1, but with stacking method, I divide into 2, so it has 2. Stacking method, how it reduces power is that it has a stack effect. A stack effect happens when there is current flowing through the stacking series circuit, but since there's a stack effect, so one of the transistor is off, so therefore the current flowing through the circuit reduces. So when the current decreases, therefore the power also decreases. That's why for the whole circuit, as compared to the static CMOS circuit just now, it is lower. Okay, lastly, my technique that I'm using is the combination of 2 techniques, which is the first one, a sleep inverter technique, and the second one is the stack inverter technique. I combine it and I call it sleepy stack inverter. Basically, what a sleepy stack inverter do is that it has a sort of same operation as the stacking method. It's just that there are 2 hanging transistors. The first is the hanging transistor of PMOS and the hanging transistor of NMOS. Okay, as you can see here. However, the number of transistors increases. But as I've said, how a sleepy stack works is that it's sort of the same as the stacking method. So when current flowing, and then since there are more transistors in one series circuit, and then these 2 transistors are in an off state. So when they're in an off state or in a cut off state, the current reduces. So when current reduces, then well, power reduces. That is the most basic. That is the most basic thing you should know as an electronic student, or your electronic knowledge. So you can see here, it's the number of transistor increases. So you multiply it by 9, so you get one ring oscillator. Okay, and this is my flowchart. So this is what I do, and this is how I keep up with my project. Firstly, I study the research paper, then I design my circuit, then I go to the simulation, I analyze if I'm not satisfied, then I repeat the cycle, then all the way to making a layout. Then once my layout is complete and I'm satisfied with the result, then that is basically what my research is, and this is my research journey. Okay, this is the result that I got from the mental graphic simulation. This is the conventional ring oscillator, which means that this conventional ring oscillator uses the static CMOS inverter technique. And this is the schematic diagram, and this is the layout that I've done. It has an area of 125.457 micrometer square. And this is the test bench circuit, which means that from this test bench circuit, I can simulate and I can generate the data, and I can analyze the data that I want. And the data currently that I'm taking is this power dissipation, which is 364.2951 microwatts. And as you can see, there is the waveform. As I've said, this is the conventional ring oscillator of 9 stages. So you can see at the waveform, there are 9 different types of waveform, and this waveform obeys the truth table of the inverter. So once it obeys the truth table of the inverter, which means that my ring oscillator functions properly. Okay, and this is my stack ring oscillator. This is the schematic diagram, and this is the layout. Here's the test bench circuit as well, and this is my power dissipation, and that is the waveform. It's the same thing, and from this waveform I can analyze its frequency as well. And this is the sleepy stack ring oscillator. This is the one that I want. This is the one that is important. This is the test bench circle, power dissipation, there's the waveform. The waveform looks slightly different from the from the previous one. It's because it has a hanging transistor there. So that's why it looks slightly different. And as you can see, this is the comparison table. After I've done all this simulation and with this combination low power technique, it is obvious that the power dissipation of my last technique, it is the lowest. So it's the best, so that's why I've chose that. And you see the power reduction is 99.99, which is almost 100, which is almost perfect. Okay, well, for my project, it sounds good because it has reached my objective, which is to, it has solved my problem, which is to create a device that produces something low power. However, for future improvement, well, I'd like to reduce the layout size, by reducing the number of transistors. Well, how can I reduce the layout size? For future improvement, you can reduce the CMOS technology, which is something that is smaller than 130 nanometer technology. So in industries, as I've said, for modern industries, they can reduce the CMOS technology by 65 nanometer, 60 nanometer, it varies. Okay, and this is my Gantt chart. This is what I've done. Okay, for costing, this is important. An average license of Mentor Graphic costs 5,000 ringgit per year. So from that 5,000 ringgit, I divided into, for example, for one project, I make the one project for 1 month. Okay, so let's say for 5,000 ringgit per year, I divided into 12. So for 1 month, the license costs about 416 ringgit and 65 cents. And I'm charging 50 ringgit per hour for my service. Okay, so 50 ringgit my service, and for 5 hours means in one day I spend about 5 hours. So for an average of 20 days, I do my project for an average of 20 days. So I multiply them. So for one project, which takes about for 1 month, the cost is about 5,416 ringgit and 67 cents. And this is the most basic, the easiest project. So let's say when my project is complicated, it has a more intricate design, so maybe I'll take about 3-4 months, then this can multiply according to how many months it takes. So it's actually very costly, but for freelancer, this is a good amount as compared to when companies have to be in contract with IC designers companies. So it'll cost more than this. So this is basically one of the cheapest price. Okay. So in conclusion, the technique that I've done was a sleepy stack inverter, and that was the optimization technique that I chose. It has 99.9% reduction, so that is very good. Okay, however, as I've said, there are project limitations, which is that I cannot go smaller than 130 nanometer technology due to the restriction of the simulation that I'm currently using. This is the reference paper. That is all from me. Thank you very much.